Gamma decay. You know, in the last videos, we talked about alpha and beta decays. I said in the case of alpha and beta, we have a spontaneous decay. We can say a natural decay of any radioactive nuclei, okay? Nucleus. So we have an unstable radioactive nucleus will decay to a more stable nucleus by emitting alpha particle, you know, He42, or beta minus, beta plus particles. So here we are talking about particles emission. But when I talk about gamma decay, it will be not the same. Let me explain, first of all, the definition of gamma decay. You know, in general, after alpha or beta decay of parent nuclei, let me take an example of parent nucleus X. It's an unstable nucleus will decay to Y star by alpha or beta decay. Okay, why we have a star? It means this daughter nucleus is in the excited state, not in the ground state. Okay, so this daughter nucleus will decay by gamma decay to the lower level. This level, it can be the ground state or any lower level, okay, by emitting gamma ray. So during gamma decay, we have a gamma ray emission. You know, gamma ray, it's an electromagnetic radiation. It's not a particle. You know, Einstein defined the light as a wave and photon. We have a length of wave, we can say wavelength, and we have photon. Okay, photon, I mean a quantity of energy, it's quantized. Okay, we come back to gamma decay. During gamma decay, we have gamma ray or gamma radiation. Let me explain this situation by this diagram. Initially, we have the excited energy EI, where we have gamma or Y star will decay down to the lower level, EF. I repeat, EF, it can be ground state or any lower level by emitting gamma ray. And here, the released energy during the transition from the upper level to the lower level, we release a quantity of energy, delta E. Okay, delta E as value equals to E initial minus E final. Be careful. Now I am talking about the energy levels, the nuclear energy level inside the nucleus. I don't talk about the electronic shells outside the nucleus. We are talking about the energy levels inside the nucleus. I will talk about this point later in details when we talk about the shell model. Okay? Okay, I give you here a simple example of gamma ray. First of all, we have cobalt 6027 as a parent nucleus. Its unstable radioactive atom will decay to Ni star daughter nucleus by beta decay, beta minus decay. Ni star is in the excited state. Okay, Ni star will decay by gamma decay to Ni. Okay, Ni is in the ground state. To have the transition from Ni star to Ni, we have two gamma rays. What I mean, we have two gamma decay. For each decay, we have one gamma ray. If we have two gamma, it means we have two gamma decays. Okay, and I is in the ground state. let me explain the situation by this diagram. First of all, we have the cobalt 60 on this level. This one is E initial. You know, for each level, we have uh, this number was plus or minus. What I mean, look, here we have this one. For this level, we have 4 plus, 2 plus, and 0 plus. Here I mean for each level inside the nucleus, we have the nuclear spin I and the parity pi. Okay, I, it can be, for example, 5, 4, 1, 2, half, any number. Okay, I will talk about this one later. And pi, it can be plus 1 or minus 1. Okay, so I come back. Cobalt is initially at this level, will decay to this level 4 plus, where cobalt will be converted to an I star. An I star is in the excited state. Okay. Uh, okay, we have this decay. We can say beta decay. During this decay, we have beta minus emission. Beta minus particle, one electron will be emitted during this transition of this decay. Now, an I star is in the excited state, will decay to the ground state by two transitions. First of all, we have the transition to this level with gamma ray, and here we have another transition to the ground state by another gamma ray. We have two gamma ray to arrive or to bring an I star to an I. Okay, so let me talk about the property of gamma ray. You know, in the case of alpha and beta decay, we have particle emission, or we can say particles emission. In the case of alpha, we have He particle. You know, the alpha particle, it's like the nucleus of helium 4 2 in the case of alpha decay. He42 is positively charged because we have two protons inside the nucleus. In the case of beta decay, we have beta minus or beta plus. So we have also a charged particle. But in the case of gamma rays or during gamma decay, we have gamma rays emission. These gamma rays are electromagnetic radiations. Okay, it's not a charged particle, it's a photon. Photon is a quantity of energy, it's uncharged. uh, so gamma rays are uh, electromagnetic radiations of nuclear origin. What I mean by nuclear origin, it means you know, we have the nucleus, and outside we have the electronic shells, KLMN. We can say like this. Okay, this one is the nucleus. And here we have KLMN and so on. Inside the nucleus, we have the shell model. We have the shells inside the nucleus. During the transition from the upper level to the lower level inside the nucleus, we can have the emission of gamma ray. So gamma ray is nuclear origin, comes from the origin of the nucleus. But in the case of X-ray, X-ray will come from the outer shells. For example, from K to L, this excitation of the atom from L shell upper level to K shell, we can get here X-ray. So we have a difference between X-ray and gamma ray. These two rays are electromagnetic radiations, but X-ray is electronic shell origin, and gamma ray is nuclear shell origin. Gamma rays are uncharged and possess a large penetrating power. Okay, let me start by uncharged. Let me take and compare the penetrating power of alpha, beta, and gamma. We have a beam of alpha, beta, and gamma, and here we have a sheet of paper, a sheet of aluminum, and we have a block of lead. Okay, P, B. Alpha particle is very weak, has a very weak penetrating power. Alpha particle cannot penetrate a paper or a sheet of paper. Okay, beta particle has more penetrating power, can penetrate the paper sheet, but it cannot penetrate the aluminum sheet. Gamma particle has, or gamma photon has a very high penetrating power, can penetrate the paper sheet, can penetrate aluminum, and also it can penetrate lead block. For this reason, in order to protect yourself from alpha particle, it's easy. Just you have to put a sheet of paper. You can block the beam of alpha particle. But in order to protect yourself from gamma ray, we need more protection and more complicated protection. What about the uncharged photon? You know, if I put a beam or a magnetic field, as you see here, into the page, and here we have alpha beam, gamma beam, and beta beam. As you see, as alpha and beta are charged particles, we have a deviation inside the magnetic field. But gamma ray will continue without any deviation because it's uncharged. The same if I take these beams inside an electric field, plus minus, we have a field E. So alpha particle and beta particle uh, have a deviation inside the electric field, but gamma beam will continue without any deviation. Okay. The third property, okay, I repeat, the difference between X-ray and gamma ray. X-rays result from transitions between electronic energy levels. As I said before, the transition between the electronic levels of the atom, and gamma rays result from transitions between nuclear energy levels from the origin of the nucleus. Okay. The next point, gamma rays spectrum give a lot of information about the spin and the parity of nuclear level. You know, we can have an information about I and pi. We can calculate the parity pi and the nuclear spin I. Gamma rays are of two types. Okay, here let me classify gamma rays to electric multiple ray and magnetic multiple ray. Okay, in the next slide, I will explain in details how can we find the electric multiple ray or the magnetic multiple ray. Just you have to know we have two kinds of two types of gamma rays. We have electric gamma transition and we have magnetic gamma transition. You know, gamma ray is an electromagnetic wave. We have an electric wave and magnetic wave. The combination of electric and magnetic will create an electromagnetic wave. Here we have the classification of gamma ray. Okay. Possibilities of gamma decay. You know, during the gamma process or gamma decay process, we release a quantity of energy delta E, which is equal to E initial minus E final. E final. We have the initial nucleus will be at the upper level, will decay to the lower level by emitting gamma ray. Okay, I will explain briefly in the next slide. I will explain in details each one. First of all, this energy can be released as gamma ray emission. It means gamma ray will go out of the atom and we can detect gamma ray out of the atom. The second possibility, this gamma ray can be converted to to one electron. You know, gamma ray will hit one electron in the outer shell, KLMN, and this electron will be knocked out of the atom. Okay, so here we have internal conversion of this gamma ray energy will be converted to one electron in the outer shell, and this electron will be extracted out of the atom. This is the second possibility of gamma decay. And the third possibility, this gamma ray will be converted to one electron and one positron. Okay, so here we have three possibilities of delta E. Delta E can be converted to one of these internal per production. You know, during the transition from the upper level to lower level, we have gamma photon will be emitted and we have a delta E quantity of energy. We can say delta E or E gamma. It means the energy of gamma photon. If E gamma is greater than 1.02 million electron volt, this energy will be converted to one electron and one proton. Okay, simply. The reaction will be gamma star AZ will be uh, will decay to gamma AZ plus one positron and one electron. Let me write the energy equation. You know, at initial state, we have the rest mass energy myc square plus the kinetic energy. And you know, inside we have the excited value of energy. Still inside, we have E gamma. Okay. You know, in the excited state, Y star has this quantity, is conserved inside. After the reaction, this energy will be converted to Y, E plus, and E minus. So we have myc square plus the kinetic energy of Y plus the rest mass energy of E plus and E minus. You know, E plus and E minus have the same quantity of mass, M, plus the kinetic energy of E plus and E minus. You know, Y star and Y have the same mass number. So the mass mc square of Y star is equal to mc square of Y. we can eliminate this one and this one. The kinetic energy of Y star and Y are approximately negligible because they are heavy nucleus. So finally, we get EY or delta E equals to 2mEc square plus TE plus TE minus. You know, TE plus and TE minus, the kinetic energy of the positron and electron, these quantities are positive. So we can say EY is greater than 2mc c square because we have this quantity plus this quantity. We can say as condition of gamma decay by internal pair production, EY must be greater than 2me c square. Okay, this is a condition to have this type of decay. And we can calculate the kinetic energy of E plus and E minus, which is equal to EY minus 2mc square. So this one is the condition, or you can say EY must be greater than 1.02 million electron volt. Okay, let's go to the second type of gamma decay. We have gamma ray emission. You know, we have gamma ray or gamma photon will go or travel out of the atom directly without any interaction with the electrons or without any conversion to another kind of electron or positron. This gamma photon can continue directly out of the atom without any interaction. This photon will carry a quantized energy h bar mu. You know, h bar is a constant value. Mu is the frequency of gamma photon, is the quantity of photons per unit time emitted out of the atom. Here, let me calculate the angular momentum carried off by gamma photon. You know, the gamma photon has a quantity of angular momentum L. We can say we can identify the emitted gamma photon by its angular momentum and its parity. Okay? You know, here we have the upper energy level has a spin I and the parity pi. We can say I initial is the spin of the initial state of nucleus. We can say the angular spin of the initial state. The lower level has I final or the nuclear spin of the final state of nucleus. And we have the emitted photon has L angular momentum and pi parity. Okay, here we have pi initial for the initial energy level, and we have pi final of the final energy level, and we have pi of the emitted photon. In the next video, I will talk about the calculation of L and pi. Here, as vector quantity, L equals to I initial minus I final. As magnitude, L has a range between the absolute value of I initial minus I final and the absolute value of I initial plus I final. What I mean by this one, uh, I take an example. If I initial equals to 5, okay, let's say we have 5 plus and I final equals to 2 plus. 5 is I initial and 2 is the I final. So L will be between 5 minus 2 and 5 plus 2. Okay, we can calculate this one will be 3L7. So the possible values of L will be between 3 and 7. We have 3, 4, 5, 6, 7. These are the possible values of L. L can take any value of this one. Okay? Okay, now you know the values of L as magnitude and the value of L as vector quantity. Now let me calculate the selection rules of gamma decay. In general, L must be greater than 1. Here we have the absolute value of L. You know L equals to delta I. So the magnitude of L must be equals or greater than 1. L cannot be equal to 0. Okay? If L equals to O, we can say no radiation. We can say no gamma decay. Okay? So L must be equals to 1 or greater than 1. This is a condition. Here, let me identify gamma transitions. What I mean by this one, we can classify gamma transitions according to the value of L. Okay? For example, if L equals to 1, we can say we have a dipole gamma transition. If L equals to 2, so we have a quadruple gamma transition. If L equals to 3, we have an octuple gamma transition. These classifications are called multiple order of gamma transition. Okay, so if I ask you to classify the transition according to the multiple order of gamma transition, so it means you have to find L. Okay, if L equals to 1, you can say we have dipole transition. If L equals to 2, we have a quadruple transition. If L equals to 3, we have octuple transition. If L equals to 4, we have another kind of transition. Okay, so here you have to know multiple order of gamma transition. I mean, we have to classify the transition according to the value of L. The second point, I can ask you to find the nature of multiple order here. What I mean, uh, if L equals to 1, we have dipole, but this dipole can be electric or magnetic. Okay, you know we have an electromagnetic radiation. So for each value of L, we have this value can be electric transition, or it can be electric dipole or magnetic dipole. It can be electric quadrupole or magnetic quadrupole. It can be electric octupole or magnetic octupole. Okay, so here we have to precise the identity of L if it's dipole, quadrupole, or octupole. The second point, we have to find the identity of the nature of this multiple. Okay. Okay. So here we have two types of multiple. Multiple, it can be electric or magnetic. For example, If L equals to 1, so it's dipole. Okay, so here we have a dipole transition. L equals to 1, it can be electric multiple transition. It means we can say electric dipole transition. We can say E1. When I say E1, it means we have an electric dipole transition. Or it can be M1, it's magnetic dipole transition. Okay, so here we have two possibilities. It can be E1 or M1. It cannot be E1 and M1 in the same time. Okay, also if L equals to 2, here we have quadruple transition. Okay, quadruple, it can be E or M. E2 or M2. So L equals to 2. It can be quadruple, electric quadruple transition or magnetic quadruple transition. The same for L equals to 3. Here we have octuple transition. It can be electric octuple transition or magnetic octuple transition. Each time we have or, okay, or. So for example, for L equals to 1, it can be E1 or M1. The same for L equals to 2 and L equals to 3. So here, to classify gamma transitions, we have to find the multiple order L, and we have to find the nature of this multiple order, okay, electric or magnetic. This is in general, it's very important point of this chapter. We have to find L, the value of L. The second point, we have to find the nature of this L. For each value of L, we have to find the nature, electric or magnetic. Okay. Okay, here we have an example. For L equals to 1, gamma transition can be electric dipole or magnetic dipole.